All right. Okay. This is, we seem to have failed in our advertising for this week's one, so apologies to everybody. Um, okay. Cool. Cool. Well, this actually suits me because I lost my voice at the weekend, so I'm going to be a little bit more gentle this week. But hopefully you'll still find it useful and interesting. I don't have a Slido set up for today, so just stick comments in the chat if you have any in the Teams chat, and or just ask me in person, and we'll do it that way. Okay. So I had promised to talk a bit about um, why like AI research was sort of moved from being obviously a university dominated thing to being a company dominated thing. So when obviously research, when I did my PhD, there were a number of players in the AI world, which I talked about before, like Andrew Ng, who was one of his pioneering things was to try to make AI more commercial. And deep learning was just starting to be exciting. And there's a really cool website called fast.ai, which will teach you in about 2 hours how to train a computer vision neural network to recognize things, which is very, very cool. Very, very cool course. The person who's running that Jeremy Howard, I think his name is. He's gone on to have a startup and funding and things like this. But I don't know whether it was COVID or what, but Fast AI was obviously about teaching people deep learning very, very quickly. And I found it very inspirational because, as I probably talked about before, the traditional educational route of teaching everybody in the chronological order in which ideas were discovered, I'm not a big fan of, basically. And Fast AI, for me, embodied this like radical new way of teaching people things, which was get something working really quickly, and we'll sort of tell you about how it works as you're going, basically. But lots and lots of agency very quickly. And one of the reasons this is so important in AI is that the newer techniques are, particularly deep learning era of techniques, are radically different from the ones that came before, in the sense that it doesn't help you hugely knowing the old stuff. So everything that I studied for my PhD is considerably less relevant than it used to be. Um, but FastAI was part the way that I teach in QLab, basically, which is like do it really quick. Um, and this also marked this point at which the nature of the task changed, right? So typically in research, particularly in computer science research, tends to be dominated by people who are very good at maths, um, and particularly the more competitive kind of areas. And you still find that a lot of the people at OpenAI and stuff like that have these great maths qualifications. But it shifted. One of the crucial ways that it shifted was that most of the large language models have very, very similar algorithm underneath them. And yet they vary enormously in how effective they are. And there's a famous thing called the bitter lesson. I think it's Rich Sutton, who's a reinforcement learning expert, Turing Award winner guy. And his thing that was called the bitter lesson was basically saying, if your way of solving a machine learning AI problem is such that um, you can easily parallelize it, you can easily scale it up. You can scale it up to work with massive amounts of training data. That technique will outperform a cleverer method or a more complicated method that a human has created. And I was observing that even when I was doing my PhD for computer vision, which was that we were quickly seeing techniques that were designed by somebody. What typically would happen is somebody would look at a problem like detecting edges in an image or something like that, or a pattern in an image, and they would try to design or formalize the task mathematically, and then they create an algorithm that sort of solved the mathematical problem. And then they'd say, oh, look, I've made the best edge detector in the world, and I've proved that I have, which is an absurd thing to say. I mean, I may be making a straw man here. They may not have actually said that, but a lot of people got that feeling. It was like, oh, this clever person who's clever at maths has proved this complicated thing, and therefore it must be better. So the underlying premise of a lot of that, a lot of probability, a lot of AI was dominated by probability people, maths people, causality, all these fields. They all had this particular worldview, which was that very similar to physics in a way, where it was like, um, I'm going to make some assumptions about the state of the world. I'm not going to focus on those very much. I'm not going to like dwell on how true they are. The old stereotype of a physicist treating everything as like a spherical ball or something is the example. But and they're going to pretend that that's the way the world is, and then they're going to do an awful lot of work to work out like a perfect solution for this pretend version of the world. And it turns out for lots of real problems in the world, that doesn't work. And the reason it doesn't work is because the simplification is wrong. The assumption about the state of the world is wrong. And the way you find out whether it's wrong or not is you perform experiments in the real world with real data, and you see that that mathematical approximation doesn't achieve the goal that you're trying to achieve. And effectively, machine learning, which when I was doing it was still a somewhat controversial field, um, is the idea that, well, why do we bother with the proof bit, right? If we have to perform experiments with real data to tell us whether it's working or not, why don't we just use a computer program to sort of search for a way of representing what we're trying to do? And why don't we use something called backpropagation, where you basically start with an algorithm that doesn't work at all. It's like random noise, basically. And say it's trying to find edges in an image or something. It just gives you random pixels in the screen, tells you they're an edge. And then you have a correct answer where a human has manually labeled the correct answer. And then you say, okay, well, this algorithm has not produced the correct answer, but we know how to subtly change it to make it more correct. And that's basically machine learning. And deep learning is a type of machine learning. It's a type of machine learning which has this magical property about it. So when I was doing AI for my PhD, a lot of people had these theories, which are things like if you have this certain amount of ways that something could vary, then you need a similar quantity of training data to reflect that variation, right? There was this belief that this was the way things worked. And then deep learning came along and broke all of those rules, basically. It said that you could learn, a huge amount with, with, with a much larger set of weights, something magical was happening. So you could take a set of weights and then that took up, 20 gigabytes of storage or something, and you could pass through those weights terabytes and terabytes of examples. And somehow this 20 gigabytes would still be able to retain much of the information that you'd passed through it. And that was completely strange and weird and counterintuitive, basically. Sorry. Cool. Um, and it was very, very strange. Oh, here we go. And one of the things, so why did that happen, right? So this discovery emerged, and it emerged out of Geoff Hinton's lab, and they made this thing called AlexNet. And I may have talked about some of this before, but it's an interesting story. So what was happening in computer vision at the time was people were trying to make computer vision more and more capable. So the traditional way of doing AI research, which is a practical technique today, is to, you're trying to do something, whatever it happens to be, you make an artificially small example of this, a simplified version of the problem, so simplified that it might be completely unrealistic or impractical. And then you try to get the AI to do it. So an example of this in the early days of computer vision was, here are like 5 different types of things that we want the AI to be able to recognize, right? Here's a chair, here's a plane, here's a tank, used to be funded by the military, you can guess, and things like this, right? And you would try to use machine learning to predict which one it was. Now, something called ImageNet was created. ImageNet was an attempt to create a much, much more difficult task than had been done before. Because what typically happens is in academia, the best way I would describe academia is that it's somewhat like the Olympics, right? So academia is not really about solving problems. So one of the things about academia is that the people within it, the majority of people within it, have never experienced anything but education. And then they have this system called peer review, where you basically write a paper and other people that are your peers, other academics, look at the paper and decide whether it's any good. So when you have a system like that, where you don't have a method of judging success that is formal, like we're not collectively trying to get to the moon or anything like that. We're just doing things that other people think is clever. So what happens in academia is you get this bias towards mirroring the way education works. So basically most academics are operating as sole individuals, particularly in computing. And just like they have to sit down and do an exam or something like that, they have to be able to do all the questions, right? Unlike in a company where you have a number of people with specialized roles working together to achieve a goal. And then the way that academia goes is that you have these ritualized patterns of working, usually ritualized patterns of working that are sort of gatekeeping. So in the social sciences, for example, you have to know special unintuitive meanings of words, for example, and by using them appropriately, you demonstrate that you are qualified to be talking about something, right? If you are in machine learning, then you would follow certain approaches. You would produce certain graphs, you perform experiments in a particular way. And I may have mentioned this before, I was in biometrics quite some time ago, and in those cases, depending on how old your biometric was, the number of example images or experiments that you had to do was either like completely unprofessional or very, very rigorous, and the number was completely arbitrary. And that's why I say it's like the Olympics. You're basically taking a group of people and enabling them to sort of, in a secure way, protect their specialness, if that makes sense. And you're making a completely arbitrary activity that achieves that goal. And usually people like do well at university, in certain directions. Maths is a good test of that because people think, oh, maths is a bit like IQ test, a bit like being good at chess or something like that, right? The side effect of all of this is that you get a quite weird prioritization of activity. And so AI was fine for years and years and years because very few people made any money out of AI. So there's all these research fields that are sort of stable and prestigious and long lasting, largely because they're not useful. Because once they're useful, it's no longer the community who is judging whether something is good or not. There's now some external force having this influence. In the case of machine learning, there was this constant tension because machine learning inherently was a little bit transgressive, right? It was saying instead of somebody else who's good at pure maths looking at my paper and saying, I'm a good boy for doing pure maths the way they liked, um, now we were going to perform an experiment in the world. And if I happened to achieve a result in that experiment that was better than somebody else who was better at maths, then like my work should be promoted and shared, right? And so that's a little bit transgressive. And then ImageNet and the introduction of like deep learning was an even more transgressive idea, because in the transition that I was around for my PhD, we still had like two camps. We still had lots of people doing the pure mathsy stuff, and then we had people doing the machine learning stuff. And the pure maths people were like constantly kind of like trying to formalize the things that machine learning people had pragmatically found to be useful, basically. We had this kind of ecosystem. And then ImageNet comes along, and it's basically a continuation of this idea where the task keeps getting harder. And so what people would do in order to be relevant and useful was they would create a new form of Olympic competition. Most of these competitions were still far from being practically useful in any specific situation. They were just like, this is harder, and it's suitably harder so that lots of people in the community will try and do this, and therefore we can say this person's better than this person for doing it. But it was still really artificial. Like ImageNet itself had a very large number of images of different breeds of dogs, but it has like one category for like church. I think it has one category for shop, right? For example. So it's not in any way aligned with a practical problem someone might have, or with the general concept of like what are things that people see in the world and it would be important for a robot to understand, for example. So most of these competitions are like super fake and not linked to anything useful. And from the community's perspective, from a power dynamics perspective, it's actually useful if the research is useless, because it's easier to maintain and control the power dynamics of groups in that situation. So ImageNet comes out, and you know, wasn't a particularly revolutionary idea to do it. It was just the natural continuation of making things harder, basically. Um, and then AlexNet is produced. And what AlexNet is a combination of a graphics card with deep neural networks that existed before. This just scaled them up. And so this technique was substantially better than everyone else. So you imagine like you're watching the whatever the Olympics, the sprinting. You can tell I'm a big guy into sport, and whoever it is winning. They're winning by like tiny fractions of a second, and they've done that for years. And then somebody comes in and they win by like 10 seconds, which is probably impossible. But you know what I mean? That's kind of what it was like. And the problem is that deep learning represented an a very great continuation of this idea that the special ideas of the person coming up with the technique were less important. It was even less designed in a way than other forms of machine learning, even less proofs about it. In fact, it almost seemed to be a contradiction of proofs that already existed about what was possible to be learned. So this comes out, and there's this great period of tension between a lot of the people who are prestigious in artificial intelligence and even in machine learning, and the people who have empirically made a lot of progress. And as is frequently the case, the Americans, you know, take take this idea and commercialize it in a very successful way with OpenAI. Now, OpenAI wasn't actually where it began. Where it began was DeepMind. So DeepMind actually comes out of the games industry, my old stomping ground, and Demis Hassabis founded DeepMind, which was like a really impractical thing, right? It was very unclear how DeepMind was ever going to make any money, how it was ever going to do anything particularly practical. Andrew Ng had sort of cornered the market on industrially useful computer vision, and DeepMind was just doing like it was creating AIs that could play computer games. And it was like, when would that ever be useful, right? So of course it was quite attractive to a number of people from a sort of academic background, and they focused on reinforcement learning. But then some of the people who worked at DeepMind, they went and joined OpenAI or helped form OpenAI, and they really, again, they had no idea what they were doing. They were just like, we've recognized that there's this revolution. There's a signal we can tell that's confusing, that has upset the way these problems are being solved. And it seems like if we scale this up, it can solve more and more problems. And again, they didn't really know what they were doing and making random things, didn't know ChatGPT was going to be successful, all kinds of different things like this. Um, but what happened there was, first of all, being able to scale it up was very important. But the other thing that was really important was the data was really important. So now the algorithm itself is not the critical factor in determining whether the AI is successful or not. It is the information you pass into it that seems to make a much bigger difference. Now, we also have some later on processing, which is a little bit more complicated, but for a long period of time, it's basically the quality of the input data. But the problem from the research perspective was that that goes against what the culture was in academia for rewarding work. So for a long time, people had said, like, whatever your niche field of research is in the field of machine learning, you might say, well, we kind of know the quality of our data determines the quality of the model we produce. So if our goal is not to impress our friends, or I say friends, more like frenemies is a better way of referring to academia. But if that's not our goal, if our goal is to do something useful in the world and make progress in understanding how things work, we kind of realize that data collection is important. But data collection isn't like pure maths. It's not something that you do sitting at your desk. It's a very logistical task. It's repetitive. It involves attention to detail and various things, but it just doesn't align well with the traditional intellectual Olympics that is academia. So as a result, funding for projects to gather data on large scale and do things like that were basically underfunded. And it was very common if you did a PhD and your PhD like primarily was about collecting data, it would be looked on considerably worse than if you had made an algorithm that didn't really work very well. That was more, it was harder. It was more like what you would do to get a high mark in a computer science course or something like that. So what happened then, of course, is when it started to become commercially significant, and also that people who were outside of academia were starting to do the task, they started to realize, okay, we might be able to do something useful here, or at the very least, the path of least resistance towards us making things better involves gathering data. And so a number of different companies formed sort of in the darkness that people don't know about that specialized in collecting data. And they did things like cleaning the internet, gathering data from all kinds of different sources, this whole like kind of shadow world of data collection, a lot of it iffy from a legal perspective, emerged. And the commercial industrial AI groups started making use of this stuff. And one of the big breakthroughs was Stable Diffusion. That came out before ChatGPT, I think. And so that was the first like credible AI art system. And it was trained on something called Lion 5B, which was 5 billion images scraped from the internet. They basically, they didn't care about where they came from. They were just images who had a text description under them that by some kind of metric was considered a reasonable match. And so it was as many images as they could possibly get from the internet. And this was produced by a group that was effectively a startup company, but obviously was, presented themselves sort of as a research group, but they were kind of a startup company. And so they gathered this enormous data set, and then that data set enabled the creation of the first AI art tools that kind of worked. Um, and so what happened then is the disconnect between academic practice and priorities and reward systems and what was empirically starting to work was completely different. And all of these companies were now paying these other companies that collect data, some of them in public, like iron5b, and others like Scale AI. Scale AI is notable because Mark Zuckerberg basically bought Scale AI, and that was where all the really big salaries that you may have heard of, the multi-million dollar salaries and things came from. That was hiring Scale AI. The reason Scale AI was so critically important is because data is so important to creating effective AI. So this is sort of the story of how AI moved from being a research field to being an industrial research field. Um, and there are still innovations, but the feeling I get, I'm obviously not working in those companies, so I don't know for sure, but just the signals that I'm getting from things like hiring Scale AI is that a focus on data is massively more important in terms of achieving the goal. And this overlaps with this stuff that I've talked about with agents as well. So people have asked before about like, what's an agent system? How do you make modern AI? So I should tell that story as well. So we've sort of historically, we've got to the point where deep learning is really big. Fast AI came out, taught people how to train their own neural networks on data sets. And then the frontier models started to train on data sets that you couldn't compete with at all. And they were just massively better. So lots of fields that were sort of straddling the two worlds between research and industrial research, which fast AI was like, which were where people were training their own models from scratch. They were still doing that. They were still trying to do things like that. But then what we reached was a point where, yeah, you could train your own model, but it was a very, very niche problem that you had where a foundation model wasn't just better. And so if you had a practical task you're trying to perform, you could um, like train your own thing to do it, but you would encounter problems and issues. And if you just swapped your model out for one of these big foundation models, it would typically solve the problems. This was particularly true in the whole field of natural language processing, which has been around for ages, and not made very much progress, really. And then suddenly it was a practical and realistic thing to do. And now the way I run projects changed. So it started out with the more traditional machine learning. Then we did Fast AI course and taught people how to learn deep neural networks and stuff. And then we found there wasn't really a point in doing that because any task we tried to do, if it was remotely general or commercially useful, there would be a new model within 6 months, 3 months of us starting the project. And so us training our own, there was no point in doing that. We just use something else. So we started to change the way the models worked. So we focused more, or the projects worked. So we focused more and more heavily on automatically evaluating whether or not the system was good or not. And in fact, being able to judge whether a particular foundation model plus some other library or some settings or whatever was better than another one. So the projects became more and more about basically searching and like pulling together other people's work. And this was because more and more, I was finding projects, even when Liam was doing his project, which is like 6 years ago now, that like weeks before the end of his project, a radical new model came out from Facebook, basically, and we just swapped it in, reran the tests, demonstrated it was better, the algorithm was better than it was before, and because we had used those models to achieve a practical purpose, we basically hit the state of the art immediately because we took the state of the art foundation model, had some stuff over the top, and now that was the best thing. So pretty much now that is the kind of project that I would tend to run until very, very recently. where we've started to see these agent programs. And now more and more of my projects are agent-based projects. So what's an agent-based project? Well, I talked about it a little bit last week, but an agent-based project is like describing the task in English to an AI, and you've got some sort of like main loop. The simplest kind of agent is you tell it to do something and you keep asking it if it's finished, and if it isn't finished, you ask it to do some more work. That's like the most basic agent you can create. And a lot of agents are basically that, right? So something like Lovable or something that writes a whole, you know, a whole SaaS app or something from a single sentence is doing something similar to that kind of thing on the hood. So that again is a little bit different, but it still retains this core idea that we need a way of evaluating what the system is doing and making some selections between different ways of doing something in order to make it work well. And the way I'm approaching these projects now, I mean, one of the reasons it's fun to do these projects is because I like change. And like it seems almost every year, I'm running projects in a radically different way. It's like the critical skill to have is constantly shifting and moving. And in the case of agents, one of your biggest problems is how do you measure whether something is working properly? And these days, the phrase that's used a lot is evals. They're called evals. And basically, this is some sort of method of judging whether or not the result has been achieved. Now, usually what that will require is something like getting a human to do a whole bunch of tasks that you know is an expert, and then getting the AI to do those tasks. But the tasks will usually not be like binary perfect results. You somehow got to like fuzzily match between what a human did and what the AI did. And what I've encountered many times as being a problem is how are you going to do that? If you require a human in the loop to look at the two and say which one is better, that's enormously expensive, enormously time consuming. And the more expert the task, the more unaffordably expensive it is. Now, OpenAI and the other AI companies literally pay people to do this. And you can actually make quite a bit of money doing this if you have expertise in special fields. They're paying all these like incredibly high-priced lawyers to judge between a lawyer and an AI's output. So that's the most trustworthy output. But what many people are trying to do, and I've tried to do on numerous occasions, is can we get the AI to tell us whether or not these are equivalently good? So, you know, the human constructed answer is, you know, it's hard to come to that conclusion unless you have the skills. So what you're hoping is the AI is now smart enough. It might not be smart enough to reliably perform the task, but when it sees the right answer and it compares it with another answer, it can accurately judge whether they're equivalently good. And this is not obvious that that would work, and frequently doesn't work. I've done loads of projects where we've tried to get an AI to judge things, particularly things like story generation. Is this thing funny? Is this interesting? All these kinds of things. Things like ChatGPT tend to give you the answer 6 or 7 most of the time. I mean, it can tell really extreme examples, but when you're talking about like a high end, you know, distinguishing between a, you know, world famous movie that everyone loves versus something that's kind of okay, it's very, very, finds it very, very difficult to tell the difference. However, I did run a project a couple of years ago where we tried to do this. And what we did was we basically got all the screenplays we could of the best movies that we could find. And then in those days, they weren't updating ChatGPT quite as frequently as they are now. So the current version of ChatGPT is quite up to date and can search the web. So it's very difficult to know something that it doesn't know. But in those days, ChatGPT was like time-stamped to a particular month in the year. And so any movie that came out after that month according to ChatGPT, according to OpenAI, they hadn't trained on that information. So we could use that as test data to basically say, how good is this movie? And in our case, good was something like Rotten Tomatoes score or IMDb score, something like that. Can the AI predict that? And then we can use a whole bunch of movies that it sort of knows about, and we can see if we can modify the AI to be a better critic of screenplays, which if you could make that work reliably would be incredibly commercially valuable. And so we tried to do this, and most of the time what we produced was random noise. But by accident, when the student was doing the project, they accidentally ran a training session. Now, what we were using was OpenAI's ability to fine-tune the model, which very few people use these days. Mostly they control the AIs by writing English. But in those days, it was still unclear whether you got more of an advantage by training a model. And in this very particular case, I felt that this was a very good application for fine-tuning an AI model. And so we tried it, and we tried it on 300 screenplays. And the problem is, there just aren't that many great movies in the world. And 300 is pretty close to what is broadly agreed to be really amazing movies. And so we tried that, and we got a signal. So we went from complete noise. The AI was just, whether it said something was good or bad, was completely uncorrelated with the signal. But 300 screenplays seemed to be enough screenplays that it started to get what it was we were asking it to do, and therefore it could start to learn it. And interestingly, that hasn't been a priority of the AI companies. People have talked about this for a while as being like the next frontier of AI, where instead of training AIs on completing text that exists or video or images, we start asking AI to make predictions about the world. And there's a very interesting company called Polymarket, which is what's it called? A prediction market, which is like sports betting, except instead of betting on sports, you're betting on real world events, like who's going to be elected, all these kinds of things. And that is actually formed by a group that used to be in Google. And Google said, come and work for us. We'll let you make prediction markets, and we'll like make a Google branded product that shares the world a prediction market. Because prediction markets are a fascinating tool of societal decision making, basically. So the way a prediction market works is you pick something that you can unambiguously determine in the future, and then you just assign money to yes or no this thing happening. And the story about how it happened in Google is quite amusing. They set this up internally in Google. Turns out it's a legal nightmare to set it up as a company because there's so many laws preventing gambling and restricting gambling. And even though this seems like a very useful tool for sort of conveying a potentially wise decision about the future, like we already use that in the stock market to determine whether a company is doing well or not by using the same principle, but applying it to decisions that we might care a lot about, like, you know, the consequences of global warming or, the behavior of Putin or something like that, that this would be an extremely powerful tool. And Google liked the idea of it, as do a lot of people in AI and machine learning. And so they set that up internally, and they ran it for a while. And they used a mixture of potentially useful world judgments, fun ones, which Polymarket has as well, like where is Taylor Swift's album going to place and stuff like this, and internal management of Google decisions. And because one of the interesting ideas is that in theory you could use a Polymarket or one of these kinds of tools to manage a company. So you could say, when I worked in games, I think it was, I'm trying to remember which company. I think it was Activision. Activision had like a campus, and they had this fake shop inside the campus of where they made the computer games, and it looked just like a GameStop or something. And what they did was they filled it with all modern games, so it looked like a normal GameStop. But they also filled it with the games they were thinking of making. So they made the covers and made them look totally realistic. And then they got people to go into the store and with real money, and they had to pick things to buy to completely replicate the real decision making process. And they used that to gain a trustworthy signal or somewhat trustworthy signal. They also took their most senior executives and got them to gamble on the success of games, including their own and their competitors. And this provides a very useful signal because it's this lovely thing of like, put your money where your mouth is, right? And I often think I did have an interesting conversation with ChatGPT about like, could this solve like internet rudeness? Could it become a cultural norm that basically if one person was like incredibly negative about something and one person was very positive about it, you just say, well, let's just resolve this with a bet. Let's see how serious you are about your position. And that would be an interesting way of like, cutting down on the, strange partisan debates, or at the very least, harvesting them for profit, which I thought would be quite entertaining. So anyway, the reason that, one reason why Google didn't go ahead was obviously the legal problems. And the reason Polymarket is coming into existence, I presume, is something to do as part of the deal making between the tech bros and the Trump administration, right? They're sort of letting this come through. Um, but also, the other reason was that it started to have an influence over the power structure of Google, which was fascinating. So one of the things that they had was like, well, is this product that is currently in development at Google going to hit its deadline, for example? And so they ran a Polymarket, like all the employees said, no chance of this happening, right? And they were right. They were completely accurate. But many organizations have this sort of myth-making culture to them, where the people at the top of the organization um, sort of tell stories, tell lies basically to the organization, um, or feel the need to, I suppose. And sometimes the reality of how the organization is being run is something that would be too unpalatable to say overtly, to be clear about things. Um, well, there are many reasons why this might be the case, but like in this particular case, Google decided to stop doing it. And so the people left and they set up Polymarket and got this. Okay, so what's the point of all this? The point of all this is to start to say, well, we lived in a world where being good at algorithms and defining processes and writing computer code was very important. Maybe we are beginning to enter a world where information, gathering data and interpreting data and structuring it into more specific tasks, which you can then measure the success of, is becoming the skill that everybody needs to acquire. And there's this huge disconnect between what is being taught and that skill. So let me give an example of something that I did when Stable Diffusion came out that I thought was kind of cool. And I'd really love to do a lot more of. And I think that way of thinking is kind of a way to make advances in AI and contribute to AI. So one of the things that I did was when Lion 5B came out, the people who produced it, they used a library from Facebook, which enabled you to create really, really large indexes of information. So if you had like a vector, so like 128 float vector representing a point in high dimensional space, and you had like a billion of them, then this would enable you to very quickly do like a find the nearest points query on this stuff. It was incredibly fast. And basically, modern vector databases are an evolution of that original algorithm. And so what the people who did Lion 5B did was the way that the AI art algorithms work is that they have a way of converting a picture into one of these embeddings. You know, I keep talking about these points in space idea. And the reason that you can write text and produce a picture is because they solve a problem where they take a load of images that have labels underneath them, and they learn a neural network that creates an embedding for the sentence of the label and an embedding for the picture. And they ensure that those embeddings are close together if they happen to be a picture and labeled together in the training set. And they created something called OpenClip that did this task really well. And as a side effect of building this for Stable Diffusion, you could then turn any picture or any text into this high dimensional point using this algorithm that you could run quite quickly on a computer. Less than a second or whatever, it would just give you this vector. And then what they did was they took all 5 billion images and they created embeddings for them. And then they stored them in this high performance data structure thing on disk. And then associated with each one, they had the URL of where the picture came from. And so you could run on a conventional desktop laptop Google Images effectively. You could sit there and you could type letters into the search bar, and every time you typed a letter, you get a completely new set of pictures because it would calculate the embedding basically in real time, do the search into this lookup table that lived on your own machine, and then you would get all these pictures out, which was incredibly cool. And for a long time, you could access this. And then some enterprising journalist thought, these images have been scraped from the entire internet with no human oversight. And the way they determine whether or not the images are okay is using very vague metrics of things like how fuzzy they are and stuff like that. And later on, they introduced a not safe for work detector, but that wasn't actually filtered out of the training data for Stable Diffusion. And they thought, I wonder if I search through these URLs, am I going to find stuff that people shouldn't be sharing on a public website? And yes, there was like, you know, sexual images of children in the training data, for example. And so that was the kiss of death for Lion 5B, and you can't get it anymore. And you can't get the demo anymore. Those things don't run. However, it was a very, very interesting idea. And one of the things I loved about it was unlike all my time in biometrics, where basically people were just wandering around with a camera photographing students in random lighting conditions and with scarves and glasses and hats and things. It was just completely undirected random data collection. This was like a glimpse into the unbiased probability distribution over images on the internet, which is not like an unbiased representation of images in general, but there's still something kind of cool about it, and it's enormous. So I thought, what if I could like analyze this information and create a structure to it? And the reason I think this is interesting is because I think this is the universal way of approaching advancing both agent programs and AI, right? Is that basically you take something like this and you let this incredibly intelligent AI, by looking inside it, can you understand how it has cut up the world in order to solve its problems, and therefore get some kind of profound insight into the nature of information or the nature of the world in some way. And so basically, the way this index worked was it would cluster together lots of points that were in a similar place. So this is a really high dimensional space. So like there's these little islands of points that naturally appear in this space. And so it clustered them together, and it had like something like, it was like 135,000 clusters. So what I did was I grabbed 10 example images from every cluster, and I got the point in space that was the middle of the cluster, which was actually inside the pre-computed model, so I didn't even have to do any calculations. And then I used something which is really, really cool. Actually, I love this stuff. There are two algorithms that do very similar jobs, and there are religious wars for it over which one is better. But one I pronounce as TSNE, but it's TSNE, and the other one is UMAP. And what these algorithms do is they take points in really high dimensional spaces and they flatten them onto a 2D plane, or higher if you want, but like 2D is the useful one. So you've created a map, and what it's trying to do is if points are close together, then they're close together in the 2D map. If they're far apart, they're far apart in the 2D map. But yeah, it's a sort of collapsing of everything. So I did that. And then I just made a little thing that appeared in a web page, and you could move your cursor and you could see all the dots. So first of all, you could see that, like, it looked like a real map. It was like terrain. There was clear, you know, places of higher and lower density and clear like islands of things. And then as my cursor went along, basically, whenever it hit one of the dots, it would just show these 10 example images for the points. And so you just see this like flicking of pictures as you moved your cursor around. And I was so pleased to see that with this, the way that this clip algorithm had been trained was just solving a very unhuman designed problem, right? It was solving this neural network problem. The neural network was just a big black box. There's no reason it had to lay out the images in a human interpretable way, but it was totally interpretable. It was so cool. So it was like you've got a whole section where you've got cars, and then you've got like racing cars and consumer cars and parts of cars, and then car components available for sale, and then you've got motorbikes and parts of motorbikes, and like basically rather than ImageNet, which was a very humanly biased taxonomy of things that you might have pictures of. This had organically emerged from the brains of a neural network. And so then I did further clustering on it to try to make islands out of it. And then I made centers for the clusters, and I then manually named all the islands based on what I thought they were about. It did all kinds of interesting things. So, for example, people was an interesting one. So what you got was tiers of A-lister, B-lister, C-lister islands. And what do I mean by that? Well, if you were Princess Diana, then you had an island. You had Princess Diana Island, right? But if you were like a B-lister, I'm trying to think of a good example of this. So Shannon Doherty, I think, was one of them that I remember. So there would be a set of actresses or actors who you knew from movies were somewhat interchangeable. Like they didn't have that stellar star power. They were sort of like they looked similar, their hair looked similar. It's kind of hard to tell which one is. And basically they would have their own island. So all of them would be almost indistinguishably located together. And maybe that was because people were mislabeling them in the data set. I don't know. But you got this. And then you started entering different islands. And the one island which would be like age and race, basically. So you'd start to go, okay, well, this person is no longer recognizable as a named person in the world. They're now part of these different groupings. And so like these dominant kind of like sort of racial groups were appearing and age groups were appearing as like islands in it. But you also started to get just a feel for like what filled the internet with imagery. So for example, a massive number of images were slides. Absolutely massive. Because slides are like really noisy, really different from one another. There's very little, to like tie them together other than their random text in front of things. And so you have this sea of like ugly slides, which is just taking up a huge fraction of the internet. So yeah, you got all these different sections, and I've always been fascinated by the formalization and simplification of the world in a grand way. And this was just such a cool way to do it. And what is practically useful about that? Well, if you think about what's going on there, you can now see these are the things that the AI art is going to be good at making. Anything that has an island, it's going to be good at. And if there's anywhere where it's not very good, like mopeds or something, you can see with this kind of map that I can run on my own computer. I can generate on my own computer. I don't need like crazy resources to do this. You can see, okay, well, maybe this island isn't quite as big as we need it to be. Let's get some more images in that area and it'll get better. And we can guess how good it's going to be based on how big the island is. And we don't need to like, certain areas like, for example, cars that people seem to care a huge amount about. There's so many images there, it's very likely it's generalized really effectively across that domain. And so even though there isn't exactly images on a particular car, it's got so many other points there, it's probably going to work out well. And so now you have a way of systematically understanding this incredibly general tool and where it might be having problems. And when it does have problems, you can just take the point and put it on the map and go, is that what I expected, given the density of knowledge in that particular location? And I still think it's amazing that 5 billion images, I mean, the reason they only produced 5 billion images was because they ran out of things to scrape, right? Like 5 billion is a crazily big number. So, and you're like, yeah, I'd love to do that with text. Of course, the thing with Lion 5B was processing all of the 5 billion images into their embedding costs money. So like you need a company to pay for it and stuff like that. But I think that we just haven't anywhere near done enough of that sort of stuff. And the idea of making AIs in the modern world, to me, is basically what is the thing that you're trying to do in the world? Is there some way of collecting data about that activity that you can then map in the similar way that I did with the images? So one of the biggest projects that I'm running at the moment is trying to automate IDEs, right? So we have AIs that help people to program. Is it possible to automate the manager of that programmer? And that's what we're trying to do. In order to do that, we basically want some kind of taxonomy of all the things people do with an IDE. And if we can do that, maybe we can make this map that somehow, in a vaguely unbiased way, reveals to us what people are actually doing. So the people working on this project are pursuing different theories about how we can do that. So one person, for example, is looking at Git commit histories. Can we read the text of commits to GitHub repositories to see an insight into like that's something someone's done? We know it, they've done it in the real world. Can we like create embeddings for that or something, or just process it a lot with large language models to try to extract some kind of map of all the things that people do to check stuff in? The thing I love about these sources of data is, again, it's not somebody's idea imposed on the world. They sort of naturally emerge from studying the world as it is. And every time I produce these things, they always change the way I think about the world. And that's one of the reasons that I think that in a way that feels to me like a new form of academic research. It's like we should be analyzing our neural networks and our massive data sources, and we should be reflecting on what that tells us, because the AIs are solving these relatively pure objectives, and they found it useful to structure the world in this way to have this agency in the world. Like I'd love to be able to process like all of YouTube and see what that looks like and things like that. But anyway, unfortunately, since Lion 5B, which was in the early days of deep learning, where the feeling was the winners were going to operate like Linux. So basically, in the world of computing, almost all the top algorithms in the world are open source algorithms. So it turns out if you want something done really, really well, getting the best person in the world to do it as their hobby is kind of the best way to get the result, because corporations and organizations seem to get in the way when it comes to like making really good computer programs. Maybe not usable computer programs, but like technically sophisticated ones. And so most of the world is actually built on free software. So the idea at the early days of Stable Diffusion and like ChatGPT coming out was, in the end, open source will win because it's always won before. And effectively, China is following that strategy. And they are, I saw like an empirical measurement. There's some very, very nice trend lines showing they are 7 months behind. So they are giving away a completely free version of 7 months ago's state of the art in AI algorithms. And if AI continues to work the way a lot of other technologies work, we should expect a kind of S-curve shape. So at some point, which we may have already hit to some extent, the AIs will become so good at what they do that we can't really tell the difference. I think a lot of consumers can't tell the difference between the most recent updates and the last update they had. They can't tell that it's better or worse. You just see their personality changing or something like that. Many of them don't like it, but they don't actually have problems in the world that the new level of model is helping them with. And so if we imagine that, then it is likely that in 7 months' time, the open source version will match that. And although there's improvements in investment in this particular direction, it may not help very much for many practical tasks. And one of the things that I'm curious about is whether or not we start to see that the grouping together of agents, as we do with human organizations, might be a much more efficient way of getting further, or imposing on agents like a software engineering practice or something like that, which is how humans perform in a superior way, is better than making one person really clever. Because in general, very high agency organizations don't seem to be the smartest person in the world plus some helpers. They seem to be something other than that. And maybe we can learn that by understanding training data, for example. Like what does it mean to be capable in the world? How much of your brain should you allocate to different problem solving or modeling of different things in the world in order to be effective? We now, for the first time ever, have the beginnings of a means to learn that. A year ago, Anthropic came out with, and then OpenAI very quickly came out with something very similar, or maybe it was Google, I can't remember. I think they all touched upon it, something called mechanistic interpretability, this was the way of looking inside of a large language model and starting to understand how various concepts were embedded in it. It was a very, very cool demo where you could adjust they would sort of learn collections of weights, and they would represent something like doubt, or I don't know, a concept like royalty or something like that. And so what you could do is you could delve into the mind of the AI, give it a task, and then artificially enhance that little bit of the network. And then the output would be styled using that emphasis. So it is a wonderful video on this from Welsh Labs. If you've seen those, I've sent around a link to a couple of them, and they have a cool demonstration of this where you can sort of recognize questioning on something, and they turn it up, and then the comments about the quality of Wikipedia starts being much more negative about the quality of Wikipedia because they've intensified this sort of skepticism internal concept, if that makes sense. And I think it'd be amazing to see that as an actual tool. So instead of just getting an answer back, you got an answer back with like all these like adjustable dials and things to like influence it. That again is a little bit of a tangent, which I'll briefly touch on and then wrap up because we're getting towards the end anyway. So yeah, the core of my message is basically that I think there's so much more that can be done by analyzing data than there is than analyzing algorithms, and that letting what the models are learning be reflected back to us and then using that to prioritize the data that we collect and more deeply understanding the nature of the tasks we're doing, you'd be amazed the ratio of time use that people spend trying to make a solution versus trying to measure and understand a solution. So in my experience, you get massively more out by spending more time on the measurement and the understanding and the data collection than you do on the algorithm. So yeah, yeah. I was going to ramble on about something else, but I think that's probably a pretty good point to stop. So thank you all very much for coming, and I apologize for the logistical our logistical oversights. We didn't have an advertised event today, but hopefully you found some of that useful and interesting. Just before we finish, does anybody have any questions or comments? No, no. Everybody wants to be quiet. Okay, no problem at all. We'll catch up again next week.